Welcome, everyone. My name is Raj. I'm with Schlumberger. I'm the kind of fancy title here, Delphi Data Ecosystem Manager. Today, I'll talk about the Petrotechnical suite of applications and how we brought them onto the Google platform, some of the challenges that we faced and how we work with Google to address these. But before we start, let me give you an introduction to Schlumberger, particularly for people who may not be from the oil and gas industry. We are the leader in the oil and gas services space. We have about 100,000 or so employees. We are in about 85 different countries. From the software segment, which is what I represent, we've got about 70,000 Petrotechnical users that are using this. We have around 1,600 people out of Schlumberger in the software segment, and about 800 different individual clients that are actually using this software. So when I talk about software, what do I really mean? What are these domains, and what problem spaces are we tackling? So if you look at the upstream exploration and production, that's what E&P here stands for, and the challenges in this space, you are looking at understanding of the subsurface, identifying of the reservoirs, then onto the execution phase in terms of drilling and completions first, and then into production and the operations phase. So our software suite, as you can see with the different branding names down below, goes across the spectrum, all the way from the exploration side into drilling and the production, not to forget the economics aspect of things, right? And there are some infrastructural products, which I'm showing in the last column, that are really geared towards how do we wrangle the data, how do we bring the data into these platforms so the users can work on that, if you will. So, a few years ago, the industry sort of hit a hard spot in terms of the economic stress, if you will. So the industry's goals really changed, if you will, right? So efficiency and the ability to have cost control or doing things in a much more cost-effective way than we had done before becomes a key aspect for us. And therefore, what we were looking for is how can we tap into all of these cloud and big data technologies, if you will, and sort of bring them into the oil and gas space, particularly in the upstream E&P, and how we can tap into this, right? And traditionally, where we've been strong is sort of the physics aspect of things, if you will, shown by the domain, both in terms of the human services that we do, in terms of data acquisition or the execution of the operations themselves, but also in terms of the software that we provide to the various groups. So effectively, this was sort of trying to marry the expertise that we have in the domain and the science that we have within our software, and see how can we complement this with some of the things that these cloud technologies can bring into the space. So hence was born Delphi. So this is something that we commercialized to the marketplace last September. We had a global forum, a similar sort of event with our customers in Europe, and this was released back then. So like I said, the key aspect here was to try to bring in aspects around the cloud in terms of the scalability, in terms of tapping into the data itself, right? So there's so many things that you can do with respect to the physics side of things, but when you are trying to drive efficiency to the next level, you want to see how much can we do in terms of automation, in terms of taking away the mundane things that whether it's the geoscientist or whether this is a reservoir engineer or a production engineer will have to go through on a day-to-day basis, right? So sort of bring the data science aspect of things and supplement that with the physics that is there within our platforms to deliver more in terms of efficiency and bootstrapping the users. So what I'm showing on the far right or the key quality attributes that we were looking for and what our customers were looking for. Obviously, as we are tapping into the cloud, we need to make sure that the system is secure. This is, in fact, particularly in the exploration space, a lot of what our customers are doing and how one customer differentiates themselves with the other is in the way, in their know-how of how they're processing the data, how they're able to go through an exploration phase, how they're able to identify the reserves properly, if you will. So this becomes a key differentiating factor. So if data becomes a key differentiating factor, and we're talking about the cloud, then the security aspects becomes absolutely key. And this is an aspect where we've spent a lot of time. So this is one of the architectural principles that to us is non-negotiable exactly for this reason, right? So everything else in terms of functionality, all the things below that you see on the list comes after we made sure that the system is secure. Data-centric is what I touched upon in terms of being able to bring the data science aspect of things and then supplement that with what our platforms are able to do. Openness and extensibility becomes a key aspect. So in our current suite of applications, we have a extensibility platform that we call Ocean. So these are a set of APIs by which our clients, third party, in fact, there's a lot of competitors who have tapped into it as well to bridge their offerings into what Schlumberger has been bringing into the marketplace. So the same concept has to extend into the cloud. We realize that our customers are working on things that's way beyond just the set of tools and workflows that we are going to be providing to them. And the other aspect of the cloud that we can sort of tap into is the collaborative and the personalized aspect. So unlike other industries, this is a place where you have people that are working in far-flung areas out in the field. There are people that are working in the offices across different countries. We are operating in 85 different countries, so you can imagine the challenge of distribution and collaboration that is necessary. The expertise typically lives in the headquarters, right? So there are a few experts that are centralized, and then the rest of the teams are distributed. So how do you bring the right personalized interface to get them all to collaborate and work together as a team? So this becomes a key challenge. And last but not the least, a lot of these things, and in fact, there was an interesting talk yesterday that I went to where Arun from Baker Hughes was talking about what they were doing on the machine learning side. And he was talking about uncertainty. So this is a key aspect of our industry and the challenge, because you don't get to see the subsurface. So there are certain measurements that we've done in terms of well logs or in terms of seismic. So these are, or in some cases, core samples and things like that. So there is little windows of information that you get, and effectively you're trying to build a model to piece together the rest of the blanks, if you will. So as you start building these layers of information on top of each other, you are introducing and compounding uncertainties as you go through. So therefore, the ability to de-risk this when we are trying to take decisions that make a big economical impact becomes really important. And where we are tapping into the elasticity and the scalability of the cloud is exactly that. So instead of being compute limited and trying out the few combinations that I can try out on-prem today, could I burst this into the cloud and make some decisions that are more accurate, bring down the cone of uncertainty, if you will, on the various parameters. So I kept talking about the different domains and the challenges. So I wanted to sort of drill down a little bit more deeper and talk about the different profiles of users and what types of challenges. And I'm trying to map this into sort of the IT or the infrastructure speak, so then we can try to map it into where the cloud technologies can fit in, if you will. So let's start off with the petrophysicist on the top and go around in a loop, if you will. So the petrophysicist is typically working with well data, and given the boom, then you all have probably heard about the stuff that's going on in unconventionals and shale type of workflows. This now has brought up a ton of wells. Now you're talking about hundreds of thousands of wells and historical data that hangs off of this. So you're talking about millions of logs and potentially in the order of tens of millions, if not hundreds of millions, in terms of well tops and properties that are associated with it that have been interpreted by the users. So the ability to deal with high cardinality data sets and be effectively querying this, consuming this from a computation capability becomes a key challenge for a petrophysicist. And today on-prem, we are challenged by how much you can scale up the workstation for a end user, or how much we can farm out in terms of a local HPC and its compute capability in terms of dealing with these, right? So a lot of the things that I showed you in the data column with our products were really sort of focused on the high cardinality aspect of things, so sort of providing a data infrastructure that backs up what the applications would need. Then moving on down into the reservoir engineer. Like I said, the way we are dealing with data in our space is there's only a few measurements that we have. The rest is all built on a digital model that the users have interpreted on. So the reservoir engineer is a key role where they're trying to take data that is coming in from the petrophysicists, the geologists, the geophysicists, blending them all together to understand what the reservoir looks like, what the reserves in there looks like, what the properties in terms of permeability or fluid flow looks like. So then we can start to plan the drilling of a well into the reservoir and then find out how effectively we can get the hydrocarbons. So therefore, the ability to do the de-risking from an uncertainty perspective and figure out how many simulations can we effectively run to sort of bring that cone down becomes really key, okay? And then moving on down in terms of the flow assurance engineers. So these are people that are in the production domain. So you can imagine once we've completed the well and the well is starting to produce these hydrocarbons, there is a mix of materials that are coming in that will have potentially an impact on the flow. It will have an impact on the lifespan of the equipment, whether these are the pumps or whether these are the pipelines that we've laid out. So the ability to measure and monitor the various instruments that we've put in, look at this high frequency time series data, and be able to take both control decisions in near time and be able to understand the longer term impact. So we can then plan for either workovers or an alternative strategy to improve the field comes into play, right? So this is where the production engineers and the flow assurance engineers come in, and the high velocity of data that we'll have to deal with from the various sensors that's been instrumented. So then moving on to the left, the explorationists. So these are typically geologists, but they are looking at it at a much more abstract scale. So how does an oil company decide if they need to purchase a particular field? How do you know what the field is worth? So somebody has to understand the basin, they have to understand the prospects within that, and then define what a given play is worth. So effectively sort of think about this as the abstract sizing before you can judge what the reservoir looks like and get into more technical analysis of this. So therefore, these are people that are looking at very large areas, the ability to visualize the data in all of these areas, the ability to scalably access the data for this wide footprint becomes really important for them. And sort of that ties into the geophysics. So like I said, the first piece of data that you probably get into a particular area is really the seismic data. And some of the seismic, particularly in the pre-stack world, could be in the order of terabytes to petabytes. And in a post-stack world, it could be in the order of gigabytes to terabytes. So how do you effectively bring them into a space where an explorationist or a geophysicist can zoom and pan in and understand the area in a very effective manner, right? So this is where they are actually interpreting the seismic to understand what sort of faults are in there, what sort of zones are in there in terms of horizons and surfaces and so on and so forth. And that sort of leads into the geologist, who then has to take such interpreted data that is coming in from the well domain from the petrophysicist and the seismic domain from the geophysicist, and then he's building a model, an approximation of the Earth, so then they can start to figure out what the properties of the reservoir looks like in this particular area. So a lot of our customers are really looking for a way to go beyond models into actually natively looking at the data without having to have these approximations. But the models are a way to come up with a way to simplify or wrangle the problem into a manageable space. But even there, in the past where this was in the order of hundreds of thousands to million cells, it's now getting into the billions of cells. And therefore, you can now imagine simulation type of workflows where the impact of what is being produced or injected into one model cell on one time step impacts the neighboring cell. So there's a lot of coupled value extrapolation that our simulators will have to do, and at that particular scale, that becomes a real challenge when it comes to both the data handling and the compute capacity. So if I were to shrink all this into a few bullets that we can talk about in the 50 minutes today, these are the top 5 things that I wanted to summarize. So the 3D visualization from a geophysicist perspective, from a geologist perspective, from an explorationist perspective, the multi-user collaboration, and how do we bring all of these domains together so they're all looking at the data the same way and they're interpreting the same way, so there isn't a gap or a misunderstanding between the different domains. How do we handle the large cardinality of data, particularly in the well domain, and the large size of data in the seismic domain? How do we support concurrent simulations? And last but not the least, like I said, because these are global customers, they are operating across the globe, how do we deploy these services? And if we are now offering this from a cloud perspective, we need to think about availability and reliability and all the SLA aspects that comes along with it, because they are now going to rely on our service for business continuity. So the way we took the approach in here was, obviously, we started building a bunch of workflows that were tapping into the machine learning aspect of things and trying to figure out how we can provide some of these interpretation type of capabilities using machine learning. Look for patterns in logs, looks for patterns in seismic, and then use that as a precursor for delivering some of the interpretation. But the big challenge that we ran into is if you now start to offer some of these capabilities on the cloud, but then they are doing the other 80% of the work on-prem, now there has to be constant data movement back and forth for them to go from start to finish from a workflow perspective. So how do we minimize this impact for the users? How do we take the applications that they are using today, also bring them along into the cloud? So effectively, you are shifting the center of gravity of an asset team or a business unit of a client into the cloud space. So that's where the Petrotechnical suite in Delphi came into play. So this is effectively taking our applications that typically run on desktops. Most of these are Windows applications. We do have a few Linux applications. So this is where the user interface is, and this is where the users are interfacing. And then those rely on 2 types of capabilities on the back. One is around the data in terms of app servers, database servers, and so on and so forth. And the other one is in terms of the actual physics that's built into our numerical simulators, and that's what is classified as engines. So by bringing these into the Google Cloud Platform, now the user has one place to go. The data is in one place. So whether they are tapping into some of these native Delphi workflows and the native capabilities in terms of machine learning and automation that we're bringing in, or in terms of continuing their workflow in the platforms or the engines that they are used to, it's all in the same environment, right? So that was sort of the driver for why we commercialized the Petrotechnical suite in Delphi. So what does that look like? So let's take the journey of Patrick, for example. So the first thing that we figured out is, okay, what is his profile? So if he's a reservoir engineer, he logs into the Delphi portal. So this is effectively, a bunch of App Engine services and Kubernetes clusters that are running in GKE. And this is where we manage the overall interface to the users, if you will, right? So from a user experience perspective, how we manage the subscriptions, understand which client that they belong to, what data sets they have access to, and so on and so forth. And this is also the place where we've linked some of the soft services, meaning the human services, whether this is support, help, consultancy. They may want to acquire new data, in which case we can have our sister segments come in and enable them with data acquisition and so on and so forth. And effectively what the portal does is after it has figured out who the user is and understands that in this particular case he's a reservoir engineer, routes him to a production environment that you see on the right side where we've got all of his applications and all of his data stored, right? And we know that over a period of time, we need to continue to update these applications. It's not a one-time shot. So therefore, from a continuous integration, continuous delivery perspective, we also create a lab environment. So when there is a newer version of these products that we try out, if the customer has additional extensions or plugins and things like that they have built, they have one cohesive environment where they can actually test and validate the full end-to-end workflow, Schlumberger and non-Schlumberger services together, and then qualify that to be promoted into the production environment. The final visualization of the applications and how they consume it, if you will, the native workflows are all just web interfaces, and so effectively it's ubiquitous access through a browser. For some of these desktop applications that are really relying on the visualization aspects, we use thin client visualization, so effectively doing server-side rendering and then transmitting the results back into the browser, if you will. So again, taking those same 5 key challenges and then zooming it down into the Petrotechnical suite portion of Delphi, let's jump into some of the details and how we went through the challenges. So the first one is around the 3D visualization, right? This one is a key problem for us because if you look at how most of our users work, they have probably dual 4K monitors. This is where they are sitting and interpreting 8 hours a day. If you have now taken an intensive application like this and moved that into the cloud, we need to make sure that it has the same level of performance that they are used to today on-prem, right? So just to give you an analog to how we may watch a Netflix movie, for example, you may be sitting on a 4K screen and watching a movie. So it's a one-way stream of data that is coming in from the servers. In this particular case, it's actually a two-way, and it's more than one 4K screen, right? Because every time the user decides to move, pan, interpret, click, the application has to react as if the application was running on a box that's right next to him, right? So the ability to work around the challenges that the internet brings into this space, right? So whether this is things like packet loss, what's the bandwidth, a lot of the customers, and particularly some of the locations where they are operating, there's no guarantees in terms of the right level of bandwidth that they may have. So we need to make sure how optimally we can design the system so we can deliver the right level of experience with the minimum overhead in terms of the bandwidth requirement. And likewise, we also have to think about from a global deployment perspective, how do we put these applications close enough so that way the overall latency, assume that the visualization aspect, the computation aspect has no penalty. If the customer is, let's say, 200 milliseconds away, so by the time a frame comes up and the customer clicks on it and the application reacts to it, you're looking at a half a second, right? And it may not seem much, but if that's what you work on 8 hours a day, 40 hours a week, pretty soon that becomes completely unusable, right? So therefore, the ability to understand where the user is and bring the application closer to where the user is so we can bring it within a reasonable latency becomes a key deployment and operational challenge as well. So from a journey perspective, where we started was really on the K80s. Pretty soon we realized that this was more geared towards the compute rather than the visualization. And where we are now is with the P100 GPUs, and I'll talk about the different areas or the regions where we have the service deployed today. And where we'll be moving to is towards P4. And this has been a fantastic journey with Google, where they've been sort of constantly helping us through this journey. There are a few issues in terms of where we are with P100s. Because P100s, even though technically supports vGPU, is also built more for compute rather than for visualization. So therefore, there are still challenges in terms of having to bring our own NVIDIA grid licenses. And when the machines, from a Google infrastructure perspective, go through a migration event, the machines have to shut down. So imagine if you're a user, you're remotely accessing one of these applications, and a live migration event hits. Right? So that becomes a workflow issue that we are now working with Google to resolve this with the new P4 offering that they're bringing online. So this is a video that I shot on my laptop. And effectively what you're seeing here is our application Petrel that is being served out of Iowa in this particular case, and I'm based in Houston, so I've just shot it in my laptop screen. So it's a 4K screen that's being served across the continental US, and we are getting anywhere between 20 to about 30, 35 frames per second. And anything about 20, then the user's perception that this is actually remote goes away. It feels much more local and immersive. So the other challenge, like I said, was users are in different locations. How do we bring them together? How can they work in this space together? So here I am showing 3 different profiles that are working together. And in this particular case, the client environment was running out of the South Carolina region for Google, from where we were serving the applications to these different users. So this brings up a number of challenges, particularly starting with the security side of things. So how do we, out of all of these users on the internet, identify these users? And how do we identify that these are the users that also belong to the same tenant, if you will, and therefore can share data and can collaborate effectively together? So the step 1 in that was the authentication and the authorization process. So we spent a lot of time with the Firebase team and the Google team looking at how we can tap into Google's IAM. So effectively, our users are mirrored into Google's IDP. There are a few customers, including Schlumberger's own internal use, where we have federated it with Google, and where we haven't federated with Google, we go through a registration in Delphi, which effectively creates the users in the Google space. That now allows us to do a basic OAuth authentication and get all the benefits of Google's ability to look for anomalies and to validate that the authentication truly comes from the user and the location and the device from where they are trusted to access the applications. And then on the back end of it, and this is where the challenge for the Petrotechnical suite comes in, is these are applications that are running on Windows and Linux. So they don't speak a G token or an OAuth 2 token. So effectively, we'll have to sort of bridge the gap between an internet-friendly authentication token and what the desktop applications truly need. So what we do is we have a service called SAuth, or Schlumberger Authentication. Think of this as a handshake service that once Google has validated that this user is indeed Patrick from Cardinal Oil, we can then turn around and enable an account and launch the application under the user's account. And that's what you see on the far right by this thing that we are calling the tenant AD system. So that shadow identity is what we use, so these applications don't have to worry about cloud-based identities. They can still happily work in the traditional Windows and Linux space, if you will. So here's a video. Sorry about the fact that it's a little bit grainy. I think once we imported it, I lost some resolution here. But what I'm showing here is 2 users. So the user in the has 2 4K monitors, and I also opened up my laptop in there. So you can see 3 screens, 2 4K, 1 HD screen. And then the laptop in the front is designed to illustrate to you a user who is remote, that is looking at the same screen as what the primary user is. So back to that collaboration workflow, just like we are taking the output of the application and presenting it to the user in Houston, we can present the same application interface to a user that is sitting in California. So now this effectively creates a virtual room, if you will, where these people are looking at the canvas the same way, they're looking at the applications the same way. And just as an analog, if you compare this to a Skype or a WebEx or a Link type of remote sharing, these are not really built for the kind of 3D acceleration and the interactivity that you need to be able to foster this kind of a collaboration, right? So this is sort of the high end of the spectrum, and that's what that looks like. So then jumping on to the aspect number 3 in terms of the data sets and the challenges there. Like I said, there is 2 real extreme categories, if you will. One is on the large data sets. So this could be, in the case of seismic, terabytes of data that we may have to bring into an application space. So what is the overall IOPS that my storage system can support to be able to deliver that volume of data, particularly in a random I/O pattern, into the applications? And then off on the other end of the spectrum, remember the petrophysicist and geologist type of workflow that I was mentioning, where they are dealing with millions of data items in the wellbore domain. And these are really small pieces of data, but higher cardinality of data. So I'm sure you all have had the experience where if you throw, let's say, 10,000 files into a file system, you can see how much it slows down, right? So the ability for file systems and their ability to handle both large file random I/O and small and high cardinality of files, and how you deal with this from a directory and a delivery perspective sort of stresses out the system, right? So today, what most of our customers are using are these really high-end purpose-built systems from the likes of EMC or NetApp and so on and so forth. So now imagine trying to bring this into the cloud. So some of our new solutions, they have the advantage of tapping into Google's elasticity in terms of things like Google Cloud Storage and BigQuery and so on and so forth. But what do I do about applications that still rely on a CIFS file system? How do you bring the same level of performance? And these are several hundreds of man-years worth of effort put into these applications to bake the physics and the user experience into it. So it's not possible to overnight just revamp the storage and then switch it over to use a BigQuery or a cloud storage, right? So it's going to be a journey, so which means we need to solve this problem in the interim. So we looked at a number of both open source and commercial solutions. Some of the things that I haven't listed here, we looked at things like Aware, we looked at NetApp. The big challenge that we had was getting the level of performance that we need, right? So particularly in the seismic space, for the sort of visualizations that you were seeing there, we need close to 400 Mbps in terms of throughput. And it's not a single channel throughput, because this is multiple users that are concurrently running these applications, so you need multiple channels of throughput at the same time. So how do we go about doing that? So we did a number of tests with Google, and Red Hat was the other partner that was involved in helping sort out the implementation, if you will. In fact, this was one of those components that we rewrote over and over again just to fine-tune it to the right aspect. So we ended up with ZFS. This is an old component from Solaris, but in combination with Google, we were able to tune it to provide the right level of storage backend, if you will. And the other aspect is the memory. So this is sort of probably even pushing Google to the limits in terms of what a GCE compute VM's infrastructure needs to look like. So as you can see, when you're talking about remote graphics and dealing with a larger volume of data visualization, we need a high-end GPU to be able to do that. To bring enough data into memory and be able to visualize this, we need a machine that can give that user workstation a ton of memory space. So most of our users typically have, half a terabyte or 3/4 of a terabyte on their workstations today. So how do we get the amount of memory that is necessary to hold this data up and do the visualization. And then on the back end of it comes the storage and the throughput that the storage has to deliver into this. So where we are, and if you see the picture on the top left, we are sort of maxing out the spectrum of where we could be today. So for a GPU-based machine, today we can go up to 208 gigs of RAM. And again, we're working with Google to sort of push that limit even higher, getting it closer to where we need to be, which is in the half a terabyte range, right? So today it's sort of a dichotomy. You can get the high-end machines in GCE, but you don't get the GPUs. So we sort of need the GPUs and the high-end machines, if you will. And the other collaboration that we have started on is the cloud file store. So this is a new service that's coming in from Google, so we don't have to be bothered with the deployment and the management and the elasticity of the storage solution that we've put together ourselves. So jumping into the simulators, so like I said, there is a bunch of physics that we've baked into simulators, whether this is in the petroleum system space, whether this is in the economic space, flow assurance, geomechanics, reservoir engineering. So we have simulators purpose-built for each of the domains and the kind of challenges that those domains have. And what we've done with the Delphi offering on Google is we are now offering that cloud-based dynamic compute. And what does that really mean? Now I don't have to be worried about a job queue and a fixed HPC cluster size and how do we get a bunch of reservoir engineers to fit their workloads in here. If a drilling rig is becoming available and I need to make a decision within the next couple of days whether I want to employ this or not, I can go ahead and spin the nodes that is necessary, not only to do that one simulation, but also many, right? So here's an illustration of what a reservoir simulation looks like. So these are the model cells that you see here. And the two blue sticks that you see onto the left are the injectors. And you can see that as the simulation runs, you can start to see how the water is pushing the hydrocarbons out through the other wells, if you will. So this is one simulation and how you can go through it in time. But what we are now able to do with the Google infrastructure is you can take that one aspect of it and say, what are my uncertainties? What happens if the permeability that I thought was 0.7 is actually between 0.65 and 0.75? Could I run a whole bunch of these simulations for the variability in my uncertainty spectrum and understand what my P10, my P50, P90 use cases look like? And therefore, I can start to de-risk my estimate of the reservoir and the flow in a much more effective manner. So obviously, this gives us additional opportunities to optimize here. So what I'm showing you here with respect to the graph is the white area of the graph, or basically the nodes that are active at any given point in time. Anything that is blue are the nodes that are either being warmed up or being passivated. And the orange ones are the ones that are idle. And if you can't see the blue and the orange ones, that means we've done a fairly good job, and that is the point here, that when it comes to the elasticity, we don't want to have compute sitting there idle, right? And the y-axis here is in the order of tens of thousands of nodes. And you can see how effectively we are using the Google infrastructure to map to what the customer's load is. So this sort of brings both the elasticity that they want to de-risk and deal with the uncertainties that they are dealing with, and also bring the cost efficiency on the other side, so that you're not ending up paying for a HPC cluster for peak capacity and having to deal with the cost aspects that are associated with it. So that said, there are some challenges in this space as well. So today, customers have purpose-built HPC set up on-prem, and these are running with an InfiniBand back plane, if you will. So effectively, because these are MPI-based applications and they have to share data for each time step across these cells, there's a lot of communication that goes along, right? So we've tried to optimize this by trying to do a hybrid, so where we can do shared memory in cases where the compute instances can be co-located in the same node. And in other cases, we fall back to network communication over MPI. And Chris actually pointed me to the multi-ping latency that I'm showing you here, because just like everything else in the cloud, things are constantly changing. So by the time you publish a metric, the metric is actually old. So the numbers have come down on GCE, as you see in the chart here. It's a little bit dated. So the other one that we did was we compared this with other cloud providers. We compared this with various configurations that we can do on Google. There were a couple of features, and we like to think that Google did this for us, but I think it's of general benefit to the community. So one is around sole tenancy. So this ensures that we can have a set of nodes that are assigned to work together. So therefore, we can bring down the latency of the internode communication for nodes that are part of that sole tenancy scope. They also introduced the direct vert IO, which also shaves the latency quite a bit. And more recently, with the Skylake processors and its effective use of the cache and vNUMA, if you will, we've effectively brought it down. So if you look at the chart on the right side, so this is the performance variance that I'm showing across the different options. The very first column being what the really high-end HPC setup that customers have on-prem versus where we've ended up with the Google compute engine with the combination of direct vert IO, Skylake, and sole tenancy, right? So we are extremely close in terms of the high-end without having that huge cost of deployment and maintenance and whatnot, right? So last but not the least, so far we sort of looked at some of the technical challenges. Now let's look at the operational challenges. And first off, a shout out to the SRE team in Google. They spent a lot of time with us trying to help us define where we want to deploy these services, how we want to instrument these services from a monitoring perspective, how do we define the right level of service level indicators and service level objectives, figuring out the error budgets so our operations team can be more efficient, and figuring out what are the key problems that we need to focus on operationally rather than going after every problem that's going to pop up, right? So today, from a GPU perspective, we are in South Carolina, Belgium, and Taiwan. We are working with Google to expand this to other centers. And the other regions that are out there, we can support our 2D applications, but we're waiting on the GPUs for the 3D applications, if you will. So a few other things. So this was sort of a necessary evil for us to solve. I mean, if we went with a Google cloud storage or a BigQuery or whatever, the advantage is Google takes care of the disaster recovery. But when you overlay a shared file system, in this particular case, a ZFS file system across multiple nodes and multiple persistent disks, effectively the metadata, so the individual persistent disks are taken care of by Google, but the overall shared storage setup and the metadata that goes with it, we will have to take care of it. And the good thing was the ability to have snapshots on the persistent disks is something that came with Google for free, and it's very effective in terms of the incremental snapshot that it overlays and how quickly we can restore in case there was ever a fault. So the other thing that we did was around consistency and reliability. So this was a very important learning for us. On-prem, we've gotten used to the fact that machines do not go down, disks don't fail. There used to be a time when blue screen of death was your day-to-day reality, but that's not the case anymore, right? So systems have become much more reliable, and therefore the determinism of the availability or the performance of a system has come to the user as a given, right? But when you're dealing with the cloud and with the number of things that are moving, your virtual stack is way deep. We have to deal with the fact that fault tolerance is something that we'll have to build into the systems. Be able to switch over into a different node if, for example, a live migration event kicks in. And the ability for the infrastructure to allocate a resource to you also depends on the load on the particular system. So what I'm showing here with the charts is we started monitoring what the variance looks like. So if I ask for a VM to be created, user comes in, starts an application, how long before the application shows up for him? And the more deterministic, the less variance we can bring into the system, the better the user experience is. So this was a lot of work that we did with the GCE team in Google to sort of bring down that variance that you see on the various aspects. And this is around the availability of the system and being able to continuously monitor this. So that way we can use our few precious SREs and operational teams to focus on management by exception rather than having to babysit these systems, right? So we leverage Stackdriver quite a bit. So we monitor both the metrics that are coming in, and we also route all of the event logs, including the application logs, into the system. So in the past, if there was a crash or a performance impact on one of our applications, the customer has to call us and let us know this is what happened, and we have to ask them, okay, what data set, what did you do, why did this problem happen? And now effectively what we've done is we've flipped support on its head. Instead of support being reactive, it's now becoming proactive, right? So by looking at these logs, these are now creating events that trigger an alert to the operations team. So these days, by the time the customer calls, they are pleasantly surprised that the operations team is already aware of what's the issue that's going on, and they're actually working on it. So by the time they call, they're actually getting an estimate of when it's going to be addressed or what a workaround is that will restore business continuity for them. A few more things on the monitoring. So this is application usage and security. So beyond what Google does in terms of protecting the cloud and the infrastructure, we do realize that we have our own applications and our own endpoints, and there is extensibility on these endpoints. So what you see on the chart on the right, for example, is monitoring all the failed logins. So typically, it's very easy to think about the things that you want to monitor, which is the good day scenario, if you will. But we also have to be very cognizant when it comes to security on the cloud to take care of these edge cases. So anyway, to summarize, this is a journey that we went through with Google. We talked about the 5 challenges and how we are effectively leveraging both Google's expertise in this area and the Google Cloud infrastructure to tackle these. And this is a solution that's been commercial for almost a year now. And even though I have only covered a small portion of the challenges, hopefully it gives you a flavor for what it takes in the oil and gas space to bring in our software suite and bring it into a cloud environment. But on the positive side, there is a lot of advantages that our users have got on the system already. So we talked about the reservoir simulation and the benefits so far, but you can see both on the petrophysics and on the seismic space, not only with the Petrotechnical suite, but also with the other analytical solutions that we are bringing in to supplement what the Petrotechnical suite does. We were able to greatly improve the productivity. And because Schlumberger is also a big-time user of our own software for seismic processing, consulting, data delivery, et cetera, we've also improved the way we deliver our own services, right? So these are some of the stats in terms of the benefits that the Google and Schlumberger partnership has brought into the oil and gas industry. And I will close tying it back to the first slide that we started with the sort of economical pressures that the industry is facing today. The solution that we've put in here with respect to automation and bringing the efficiency is greatly appreciated by the market, right? So I think I'm fairly out of time, but if there's any questions, I can either take it now or we can take it offline.